by now you must have gotten some idea about YDSE, how to solve problems of YDSE. Okay, and let's do a few more problems. Okay, so here there are 4 questions. 4 questions are written. Okay. Okay, so I think I need to change some order here. Okay, let's start with this. This is question number 1. Okay, and this is question number 2. And here it is 3. Okay, and then we will do this 4. Okay, let's do it in this order. Okay, note on the problem. Note on the problem. We are going to discuss it in this order here. We are going to start from this here. Question number 1. Okay. Then second, third, and then fourth. Second, third, fourth. Second, third are related. They are related. Okay. First one is different from second and third. Let's do the first one first. Okay. And then second and third. Okay. Note down the problems. Okay. And I'm sure that I hope and I'm sure that I expect that you should be able to solve it. Okay, on your own. Without much difficulty. Okay, without much difficulty, you should be able to do it. In first question, in YDSE, it is YDSE, we are using a 2 wavelength. It's a mixture like red and blue, both light passed together. Okay, incident on the YDSE setup. Okay, so 2 different wavelengths are used. What will happen? What will happen? First of all, note down. If we have a mixture of wavelength, you see, if I have a single wavelength, let's say that it is a red light. Okay, red light is incident on YDSE setup. On the screen, I am going to get fringes, dark fringes, bright fringes. Okay, bright fringes will be red, color will be red. Okay, so everywhere I will see either dark or red. Bright fringe intensity will be very high, at other points intensity will be low. Okay, at the location of dark fringes I will see nothing, no light, black. Okay, that's why it is known as dark fringe. Okay, anyway, if I use a mixture, then I will have both fringe pattern. I will get separate fringe pattern. I will get a fringe pattern corresponding to this plus independent. Okay, mark this point, note it down. We get 2 independent fringe patterns on the same screen. They will be superimposed. Okay, one over another. Okay, all right. So I am going to get two separate fringe pattern. Okay, so what we have to find? First of all, number of fringes in 6 cm length near central maximum. Okay, so how many number of fringes I am going to get corresponding to this, and how many number of fringes I am going to get corresponding to this. Okay, what is total number of fringes in this much length? Okay, so I will find some number for this pattern, some for this. I simply add it. Okay, I simply add it. That's it. That will be the number of fringe pattern. Okay. Now, if you look at the second problem, minimum distance from center where bright fringe of both coincide. Now, it will happen. Let's say that I have this pattern here. Okay. So this is a central position. This is central bright fringe. Okay. At this point, path difference is going to be 0, no matter what is wavelength. Okay. No matter what is wavelength, the path difference is going to be 0 here for both waves, for both lights. Okay. So at the center, I am going to get bright fringe for both light. Okay. Now away from center at different positions, let's say that here I get bright fringe of first light, 400 nanometer, first light. Okay, then at some point here nearby I am going to get bright fringe of the second light. Okay, then this will repeat, then this will be B1, bright fringe for the second light. Okay, now this will become B2, B2. This will be bright fringe for the second wavelength. Now, at some point, both are going to coincide. So it's like both are going to coincide at the same point. At the same point here, I am going to get bright fringe corresponding to both lights. So we have to find minimum distance where both coincide. Okay, minimum distance. Okay. Now in this case, in this 6 centimeter length, there will be several positions where the bright fringe of both will coincide. Okay. So we are not considering that. Okay. If we consider that also, it will become a little complicated. Okay. So we are avoiding any complexity. We are trying to keep it simple. Okay. We are trying to keep it simple. We are avoiding this thing. Otherwise, what I will have to do? I will have to subtract all those common positions. Okay. Otherwise, they will be counted twice. We are avoiding it. Okay. So I just have to count number of bright fringes corresponding to both. Okay. So let's find it. Okay. Okay. Now, so fringe width omega is equal to lambda capital D over small d. Okay. So omega 1 is equal to 400 nanometer. So 4 and 10 minus 7, and this is 2 meter over 1 and 10 minus 3. Okay. This becomes 0.8 millimeter. Okay. This is fringe width corresponding to this light, 400 nanometer. What about the other light? This is going to be 4, 10 minus 7. This is 500 nanometer. And 2 meter remains same, 1 millimeter it remains same. What do I get? I will get 1 millimeter. Starting from central bright fringe, okay, I am going to get bright fringes for this light at every 0.8 mm. For the second light, every millimeter, I am going to get one bright fringe corresponding to this. At some point, both are going to coincide. Okay, that will happen at some point. Okay, we will do that when we discuss this. Now here in 6 centimeter length, okay, number of bright fringes n is length over omega. This we did in the previous class. Okay, plus L over omega 2. Okay, this is 6 centimeter. 6 centimeter is 60 millimeter. 60 millimeter over 0.8 millimeter plus 60 millimeter over 1 millimeter. So that's it. This is my answer. So 600 over 8. What it will be? 75? Okay, 75. Okay. So this becomes 75 plus 60. 135. This is the answer. These many bright fringes I will see in 6 centimeter length near central maximum. Okay, now what about this? Minimum distance from center where bright fringe of both coincide. Okay, minimum distance from center, that I am looking at points near center. I am looking at points near center. Okay, this is my central bright fringe. This is my central bright fringe. Okay, let's say that this is the minimum distance. Okay, at this point, I get nth n1th bright fringe of lambda 1 at this point. At the same point, I will get n2th, okay, bright fringe of lambda 2. Okay, let's say that I am going to get 10th at a certain point. I am going to get 10th bright fringe of the first one. Then at the same point, I will get, let's say, 8th bright fringe of the second one. Okay, so the order of fringes will be different. At the same point, I am getting bright fringe for both light, but the order of bright fringe will be different. It will be different. Okay. All right. Now, this distance is same. Okay. Now, what is the distance of nth bright fringe? What is the distance of nth bright fringe? what is the distance of nth bright fringe? Distance of nth bright fringe from center, okay, near center y is equal to n times omega. At the same point, both bright fringes are formed. Okay, so n will be different. N1 omega 1 is N2 omega 2. Okay, so N1 over omega 1. Okay, is it N1 over N2? N1 over N2 is omega 2 over omega 1. So this is 1 over 0.8. This becomes 5 over 4. Okay, it can also be 10 over 8. It can be 15 over 12. Okay, it can be 20 over 16. Okay, this should be integral. N1, N2. N1, N2 should be integers. Integers. Okay, what is the minimum value? This is the minimum. This is the minimum. Okay, that means what will be the order? So at a point where both coincide, understand this, at a point where both coincide, at that point I will get fifth bright fringe. Fifth bright fringe corresponding to this light N1, okay, and fourth bright fringe corresponding to this light. Okay, so what will be Y? Y will be equal to N1 omega 1 is N2 omega 2. Fifth bright fringe and 0.8. This will be equal to fourth bright fringe into 1. This becomes 4 millimeter. 4 millimeter. And see, from center, minimum distance. And this will be repeated. So every 4 millimeter, try to think about it and remember it. Every 4 millimeter, both bright fringes are going to coincide. But that will happen only near center. Okay, unless it is specified, we always have to think in terms of near center. So every 4 millimeter, both bright fringes are going to coincide. Okay, do you understand this? So in this length, 6 centimeter length, there will be many positions where I will get both bright fringes at same point. Okay, do you understand this? Now, the second one. Let's move on to the second problem. Okay, what about second? What it is? Interesting problem. Think about it. Okay, I have this YDSE setup. And this is my distance here. At any point, what is path difference? This angle is theta, this is y. Delta x is d sine theta. Any point. Theta is angular position of that point. Now the first question is, what can be maximum path difference at any point on the screen? At any point. At this point, what is path difference here? Delta x is 0. When I start moving up, path difference increases. It keeps on increasing. Okay. What can be maximum path difference? Okay. Delta x max is equal to d. When sine theta is equal to 1, theta is 90. This theta is 90 degree. Theta is 90. What it means? That means I am going to the almost at infinity. This theta is 90 degree. That means what it means is actually, we can think of it like this. Okay. This theta, you see, this theta is almost 90. This theta will be almost 90. Now where that point will be on the screen? Okay, that means at infinity. So the maximum bright fringe, the maximum path difference will be equal to this separation D here. This is the maximum path difference anywhere on a screen. Okay. In this arrangement, it is going to be where? It is going to be at infinity. At infinity. Okay. Next lectures we will see. We will do some problems. Okay. Where we change the arrangement. Okay. YDSE can be performed in different arrangement. Okay. In different arrangement. Okay. Now we will see some different arrangements. So that's it. This is the answer. Now what is order of last bright fringe? What is order of last bright fringe? Okay, so delta x maximum. Where will be the last bright fringe? At infinity or before infinity? Where it is an integral multiple of lambda. Okay, so delta x max is equal to d. It is equal to 0.8 millimeter. 0.8 millimeter. Okay. What is lambda? Lambda is 5 into 10 power minus 7 meter. Okay. What will be order of last bright fringe? Last bright fringe. Okay. Order of last bright fringe. Okay. Order of bright fringe. Okay. Delta x is equal to n lambda. Okay. Where n is order of bright fringe. Okay. So what will be n? N will be delta x over lambda. What it means? That means delta x 0.8 and 10 minus 3 over 5 and 10 minus 7. This will be 0.16 and 10 4. This becomes 1600. 1600. Okay. This is the order of last bright fringe. Last bright fringe. Okay. Order of last bright fringe. Order of bright fringe. That's fine. Okay. This delta d is this is equal to d. It is equal to d. Okay. Now, where this will be formed? It will be formed at infinity, at a point, at a large distance from center. At infinity. Okay. So what will be total number of fringes? Total number of fringes. Okay. So it's like this. It's like this. It is my central bright fringe here. Okay. At infinity, I will get this bright fringe of order 1600. Okay. And here also on the other side, at infinity, I am getting bright fringe of order 1600. So 1600 fringes, and this is zero order. This is zero order. This is B0. B0. So 1600 bright fringes below the center and 1600 above it. What is total number of bright fringes? Total number of fringes is equal to 1600, 2 times of 1600 plus 1. This is 3201. Okay, total number of bright fringes is not infinity. Understand this. It is not infinity. It will be a finite value. If the screen is very large, if the screen is infinite, then okay. But last bright fringe is formed at infinity. Okay, so bright fringe that can be counted. Okay, so n will be equal to 3201 minus 2. Okay, this is 33199. Even though theoretically I will get 3201 bright fringes, but these last bright fringes are formed at infinity. I can never reach infinity. I can never reach infinity. Okay, that means I cannot see these bright fringes. Okay, I can see ones which are just before it. Okay, I can see this. Okay, 1599. Okay, and I can see this here, B1599. Okay, so this is the number that I can count. These two I cannot see, they are at infinity. There is something where I cannot reach. Okay, I can count only these ones, 3199. Okay, that's it. Now, the second one. That means the total number of bright fringes, a very important point here. This total number n, this total number of fringes n, okay, depends on delta x max. Okay, that is on d delta x max over lambda. That is on d over lambda only. It does not depend on any other variable. Okay. Let's see. Now the third one is a theoretical question. Note it down. Note down all the problems. Try to answer it on your own. Try to answer these problems on your own. Okay. And now we are going to solve it. We are going to discuss it. Remember this. Okay. Number of fringes will depend on the last bright fringe. The order of the last bright fringe depends on this value. Okay. This value. Maximum path difference over lambda. This tells me the order of the last bright fringe. Okay. So it will depend on d over lambda only. It will not depend on any other variable. Okay. If you keep that thing in mind, you can answer these problems comfortably and correctly in your first attempt. Okay. Try to answer them. Try to answer these problems. What do you think? I have this YDSE setup. These parameters are given, small d and capital D. Okay. With blue light. Later on, we are replacing blue light by red light. Okay. So we should know what is the relation between wavelength of this and this. Okay. Now, this is my visible spectrum. Violet, this is red, blue is somewhere here. Okay. When I go towards right, from violet to red, wavelength increases. Okay. That means lambda of blue light that means lambda of red light will be more than lambda of blue light. Okay. You have to know this property. Then only you can solve it. Okay. Now the first question. Small d, capital D, both are double. Try to understand this. First question. First let me write this. Omega is lambda capital D over small d. Okay. First, omega dash is equal to lambda remains constant. It is 2 capital D and 2 small d. It is equal to lambda. Not lambda, omega. Omega does not change. Understand, this is a very confusing problem. I have this screen. On this screen, I am getting fringe pattern. I make some change and I find that omega does not change. Do you think number of bright fringes will change? It will change. In this particular case, it will change. Okay. D is doubled. Okay. Now x max is equal to D. Okay. What is the new maximum path difference? It becomes 2D. Okay. That means the order, the number of bright fringes will change. It will become almost double. Okay, because this depends on delta x maximum. Delta x, the maximum path difference becomes double. Okay, so the order of the last bright fringe will become double. So even though fringe width remains constant, okay, the number of fringes will become almost double. Do you understand this point? Okay, so number of fringes, this n is proportional to d over lambda. Okay, so n dash will be approximately 2 times of n. Approximately double, okay? Now, d is double. Why I am saying approximately? Why I am saying approximately? It is because n is equal to 2 times of d over lambda, okay? 2 times of d over lambda minus 1 or plus 1, it does not matter. Theoretical answer, let's say. Now n dash will be equal to 2 times of 2d over lambda plus 1. Okay, this will be 2 times of 2d over lambda plus 1 minus 1. Okay, do you see this? This will be equal to 2n minus 1. That's why I am writing almost doubles. Okay, understood? Now the second one. So remember, number of bright fringes will change only if either d or lambda change. Otherwise it will not change. Keep that thing in mind. Omega will change depending on this formula. But number of fringes depend only on d and lambda. That is maximum path difference and lambda. Okay? You have to remember this point. Second, d is doubled. Capital D is half. Okay. First case, omega dash is equal to lambda times capital D over 2 times of small d. Small d is doubled, capital D is half. Okay, it's like this. So it becomes omega over 4. Fringe width becomes 1/4. What about n dash? Okay. N is proportional to d over lambda. Okay. Now n dash is will be proportional to 2 times of d over lambda. Okay, so n dash approximately double of this. Approximately double. Okay, now what about this? D is halved, capital D is doubled, lambda made 1/3. So you can answer it similarly using the same logic. Okay, D is halved. Small d is made half. Lambda becomes 1/3. Lambda is made 1/3. So lambda over 3. Capital D is doubled to capital D over. Small d is half. Okay, this becomes 4 over 3 omega. Now n dash. N is proportional to d over lambda. N dash proportional to d becomes half d over 2 and it becomes lambda becomes lambda over 3, that means 3 over 2 n. Approximately, it will increase. It will become 1.5 times. It is going to increase. Okay, where this fringe width increases, number of fringe will also increase. Okay, all of that depend on D, capital D and lambda. What will happen in the fourth case here? Blue light is replaced by red light. Blue light is replaced by red light. Blue light is replaced by, here, blue light. Wavelength of red light is more than wavelength of blue light. Omega is equal to lambda d over d. Okay. If lambda increases, then omega increases. Fringe width will increase because wavelength increases. Blue light is replaced by red light. Wavelength increases, fringe width will increase. Now what about this number of fringe? It's proportional to d over lambda. D remains constant. Small d remains constant. Okay, but lambda increases. Okay, so number of fringes will decrease. Okay, number of fringes is decreasing. Not because fringe width increases, but it is because wavelength has increased. That's why. Okay, so the order of the last bright fringe that I am going to get will decrease. Path difference remains same. Delta x max, that remains same, but wavelength has increased. So the order of fringe will decrease. You understand this? Okay. Now, whole setup is immersed in water. What will happen? Whole setup is immersed in water. Okay. I have some light ray. Let's say I have this light. It is traveling in air. It has certain wavelength. Now, if it goes into water, okay, this is mu1, this is mu2, lambda 1 here, lambda 2 here. What will the effect when medium changes? Because this we have studied in refraction, geometrical optics. Those concepts you have to remember. Okay, what it is? It is lambda 1, it is mu1, lambda 1, it is mu2, lambda 2. Okay, it's constant. Okay, it's constant. Okay, so that means if lambda, if mu increases, lambda decreases. So if the same light passes into water, the whole thing, the whole setup, everything, the whole setup is immersed in water. Okay, in that case, lambda decreases. Lambda decreases, this also decreases. This also decreases. Omega decreases, fringe width decreases. Now this here, lambda decreases, the number of fringes will increase, but it is not increasing because the fringe width has decreased. It is increasing because the lambda has decreased. So at the same point, the order of bright fringes will increase. Okay, path difference remains the same, but lambda has it has decreased. Order of bright fringe will increase. Total number will increase. Okay. Width of one slit is doubled. Now what is the effect of that? Width of one slit is doubled. Okay. So if I have this slit here, okay, there is certain distance between them, small d. Now if I increase the width, okay, you see, understand this. YDSE is performed with pinholes. Like these holes, these slits are very small, very almost point-like slits we are using. Okay, so even if I double the width, this distance is not going to change. This distance is not going to change. So what will change? Intensity will change. Okay, so when one slit is doubled, so intensity changes. Intensity changes. And that's it. Okay, omega and n are constant. There will be no change on omega and n. Okay, you understand this? All right. Now, what about this last one? This we have been discussing. Okay. Now we said that this omega is lambda d over d is constant near center. Near center only. Okay. What if I move away from center? What will happen if I start moving away from center? Will it remain constant or not constant? If not constant, will it increase or decrease? Let's try to understand this. This is my slits, normal YDSE setup. Okay. Let's see, I have this one bright fringe here, then I have another bright fringe, and another bright fringe. Even if we are talking about near center, you see, even near center, it is not constant. Omega is never constant, understand this. Even near center, but near center we can take it to be approximately constant. Let's see how it is. You see, this is like the first bright fringe. What will be angle here? What will be angle? This angle we discussed, it is going to be lambda over d. Okay. Now angular position, angular width, angular fringe width here. This is lambda over d. Here also it is lambda over d. Now here also lambda over d. Okay. You see, we have taken these points near center. Even near center. Okay, all these angular positions, this angular fringe width are same near center. what will be relation between these distances? Are they also going to be same? They are not going to be same. Okay, let me explain it with a different example. Okay, let me draw this circle here. Let me draw this circle. Try to understand this. It's very simple to understand. It's not very difficult, not mathematical. Okay, let me take one radius here. Let me draw several radius at equal angles. All the angles are equal. Let's say 1 degree, 2 degree, whatever it is, they are equal. At equal angles, I am drawing these, again. Okay. All right. Now, if the angles are same, okay, then these lengths are same. These lengths are same. But what if I am moving along this line here? Okay, in that case, if I just extend it, it will become immediately clear that they are not going to be same. Okay, this distance keeps on increasing. I have one bright fringe here, another here, another here, another here. What do you see? The fringe width, the linear distance between two bright fringes, it keeps on increasing. Okay, so the answer to that part will be omega increases as we move away from the center. This is YDSE. Okay, we discussed almost everything. Okay, number of bright fringes, how fringes change under many changes, and now we are going to discuss one other aspect of YDSE, that is intensity variation. Intensity variation. Okay, let me clean this properly. Okay, if you want, you should take some break here. You see, I do not need to take any break. I don't have to stop. But if you want, you can just kind of take some break, just try to assimilate, try to recollect whatever we discussed till now. And then we are going to discuss some different aspect, okay, the intensity aspect. Okay, the intensity aspect. It's like this. Okay, let's do it through a problem. Let's do it through a problem. In a YDSE, intensities of both interfering waves is I. Find first I max, I min. Okay, very first problem. Okay, intensity at a point where first, okay, phase difference is delta phi. Okay, path difference is delta x. Okay, a general problem. We are doing a general problem. C at a point distance at a point at angular position theta. Okay, B at distance y near center. Okay, these are general problems. Third, okay, plot intensity variation. Variation on the screen. Okay. What is intensity? If sources are incoherent. Okay, in YDSE, intensity of both interfering waves is I naught. Okay, and sources are coherent. Okay, then I have to find these, and then I have to discuss. I have to find intensity if sources are incoherent. They are not coherent. Okay, what is the meaning of coherent and incoherent? I am assuming that you know already, but we will discuss it again. Okay, when we discuss this. Okay, let's try to figure out this answer here. What do you think? What is going to be the answer? Intensity. How intensity changes? Okay, let's kind of revise this. Amplitude is equal to A1 square plus A2 square plus 2 A1 A2 cos phi. Okay, this phi is phase difference. Phase difference. So I have two waves of amplitudes A1 and A2 interfering with each other. So this is going to be the resultant amplitude. Okay, now I is proportional to A square. Okay, so I is equal to I1 plus I2 plus 2 under root I1 I2 cos phi. Okay, understood? Now I max is equal to I1 plus I2 plus 2 under root I1 I2. Okay, makes sense? This is what is this? This is I max. Okay, what is I minimum? I minimum. Okay, this value cos phi is between -1 is less than or equal to cos phi is less than or equal to 1. Okay. I minimum is equal to I1 plus I2 minus 2 under root I1 I2. Now this I can write as under root I1 plus under root I2 whole square. Okay, and this I can write as under root I1 minus under root I2 whole square. Okay, do you understand? So what we are doing? We are actually solving it. We are actually solving it. Okay. Now, you see, if I1 is equal to I2 is equal to I0, let's say both intensities are same, I naught. Then what will be intensity? Then I will be equal to I naught plus I naught plus 2 I naught here, 2 I naught cos phi. Okay, this will be 2 I naught 1 plus cos phi. This will be 2 I naught 1 plus 2 cos square phi over 2 minus 1. Okay, so what is I? Is equal to 4 I naught cos square phi over 2. Okay, this phi is phase difference. Phase difference. Okay, now what will be maximum? I max is equal to 4 I naught. Okay, what will be I minimum? It will be equal to 0. 0. When both are equal, it becomes 0. Okay, do you understand this? You understand this? Now, this is also written as I is equal to I max cos square phi over 2. What do you think? Can we do that? So we got this answer. We got this. Okay, we got this also here. What will be I? It will be equal to 4 I naught cos square, this is delta phi over 2. You see delta phi here and delta and phi both are same. Do not be confused. Both are same. This is phi, this is phase difference, and this also is phase difference. Okay, there is no difference. There is no difference between the phase difference here and the phase difference we are talking about here. Both are actually same. Both are same. Do not be confused. So in place of phi, I can also write delta phi. Okay, it means the same thing. Absolutely no difference. Absolutely. Now, path difference is delta x. Path difference is, we are going to solve it, okay? You should solve it. Okay, pause the video, you solve it. Then we are discussing again, okay? We are discussing again. This will be equal to 4I naught cos square, okay? You see, path difference is given. Path difference is given, okay? So it will be equal to half times of phase difference will be 2 pi over lambda and delta x. Have you written all of this? Note it down. Note down. It's very important, okay? Note down. I'm going to clean it. You see, once I ask you to note down, I don't have to wait, okay? Because you can pause the video. I don't have to wait for a few minutes to let you note down, okay? You can note down at any moment. You just pause the video, note down. So that's it. Here it is. It is equal to 4I naught cos square, okay, pi over lambda and delta x. It's very useful form, especially this one. You should remember this. When two wavelengths, when two intensities are same, then this is going to be the resultant intensity. Okay, we are going to use this expression. We are going to use it solving problems. Okay, after this we are going to do some numerical problem. We are going to use it. Okay, at angular position theta. Okay, what is delta x? It is d sine theta. At angular position theta, this is the path difference. Now if I know the path difference, I can find phase difference, delta phi, 2 pi over lambda and d sine theta. Okay, then I write, I know intensity. It is 4 pi naught cos square delta phi over 2. Okay, so pi over lambda and d sine theta. That's how we write it. Okay. Do I need to remember all of this? No, I do not need to remember any of this. If you know the basic interference superposition concept, if you know just this, a square is a1 square plus a2 square plus 2a1 a2 cos phi, and this I is I1 plus I2 plus 2 under root I1 I2 cos phi. And this is something that you must know. You must know. It is the basic equation. If you do not know Newton's law, you cannot hope to solve problems of mechanics. The same way, this is the foundation. This is the superposition principle. We discussed it already previous year under the same chapter, interference. There we did it for mechanical waves. Exactly same thing is applicable here. This also is applicable. This also is a wave. A wave is a wave. Okay, so some basic concepts are applicable for all the waves, electromagnetic or mechanical. Okay, so it is one of those basic concepts. It is applicable for all. Okay, so that's it. Now here, distance y near center. At this point here, delta x near center is d and y over capital D. That's it. If I know this, then I can find delta phi, which is 2 pi over lambda and dy over d. Okay, so now I know intensity. Okay, 4 I naught cos square phi over 2. This is the basic equation. Phi over 2 is lambda over pi d and y over capital D. That's it. Now, plot intensity variation. This is something which is very important. How the intensity changes? Maximum will be 4I0. Which type of fringe? Bright fringe. Intensity of maximum intensity of bright fringe will be 4I0. 4I0. Intensity of dark fringe will be 0. We just found it. I max 4I0. Okay, this is 4I0 here. Minimum is going to be 0. At any other point, how the intensity changes? Okay, so let's plot it. Let's see how it looks like. Does it change like a straight line? Does it change like a parabola, circular? How does it change? How does it change? It's like this. Intensity I is equal to 4I0 cos square delta phi over 2. Okay. Now what is delta phi? Delta phi is equal to 2 pi over lambda into delta x. It is 2 pi over lambda into d into y over delta. If I want to write it in terms of linear distance, okay, that means this is my, you see, this is my central bright fringe, okay. So it is like this here. I can also write it in terms of theta. I can also write it as delta phi is equal to 2 pi over lambda. Of course it is delta. With this I can also write it as 2 pi over lambda and d sine theta. Okay, I am getting this cos square term. This cos square, okay. So first of all, it is always positive. Always positive. Okay. Now it changes between 0 and 1. 0 and 1. Okay. Now this is the graph of cos theta. This is the graph of cos theta. Now how the graph, this is theta, this is cos theta. Okay. How the graph of cos square theta will look like? Cos square theta. Now everything becomes positive. Okay. Now this intensity also is a function of cos square here. Cos square, okay. So it is going to change similarly. Now this is okay, that's how it is going to change. And this will be maximum intensity. Okay, that's how it is going to change. That's how the intensity of fringe pattern is going to look like. This is 4I0. This is 4I0. Minimum is 0. This I is equal to 0. Okay, so a bright fringe here, bright fringe, this will be a dark fringe, this will be a bright fringe, then dark fringe, okay, bright fringe, then dark fringe. This is how it will change with theta on the screen. Okay, understood? Now the last one is interesting. What is intensity if sources are incoherent? What is the meaning of incoherent source? What is the meaning of coherent sources? Two sources are producing waves, let's say of same intensity. Intensity remains same. They are coherent. What does that mean? That means, first of all, they are producing waves of same frequency. Just in case you have forgotten, you should note down. Note down. Two sources are said to be coherent if, first condition, they produce waves of same frequency. Frequency must be same. First condition. Second condition, phase difference between waves remains constant. Phase difference between waves remains constant. It does not change with time. Okay. So it is not necessary that both waves are in phase. Okay. It is not necessary. There may be some phase difference between the waves, but whatever is the phase difference, that phase difference should not change with time. It should remain constant. If that happens, then the sources are said to be coherent. And if this does not happen, even if the frequencies are same, but the phase difference between them keeps on changing with time, then the sources are said to be incoherent. In that case, will there be interference? Will there be interference? What would you answer? If sources are incoherent, if sources are incoherent, will there be interference? Answer: there will be interference. There is always interference. At a given point, if two waves arrive, they are going to interfere, they are going to disturb each other. That is interference. There will be interference. Okay, now think about this. At any point, two waves are interfering. Interference can be constructive, it can be destructive, or it can be between them, okay, any time. Intensity, the resultant intensity depends on phase difference. We just looked at it. This is I is going to be equal to I1 plus I2 plus 2 under root I1 I2 cos phi. The resultant intensity depends on phase difference. This phase difference keeps on changing. At the same point, two waves are interfering. They are not incoherent. They are not coherent. At the same point, the intensity will keep on changing. Why? Because this phase difference keeps on changing with time. It is not constant. At the same point, sometimes I have bright fringe, sometimes I have dark fringe, and it keeps on changing with time. Intensity keeps on changing. There is interference, but intensity of every point keeps on changing. So that fringe pattern is not stable, and it fluctuates so fast that you are not able to figure out if there is any fringe pattern or not, because it fluctuates very quickly. Okay. So what happens is the fringe pattern is not discernible. Okay, even if there is fringe pattern, but it is changing so fast with time that to us it appears as if there is no fringe pattern at all, and the whole screen has same intensity, same average intensity. What will be average intensity? Average intensity. Okay, so average of this intensity is equal to average of this I1 plus under root 2 I1 I2 cos phi. Okay, this will be equal to I1 plus I2 plus 2 under root I1 I2 average of cos phi. What is average of cos phi? This is equal to 0. Average of sin theta, average of cos theta is 0. Okay, that means I average is equal to I1 plus phi. That's it. And that's what you have to remember. For incoherent sources, the intensity everywhere will be equal to I1 plus I2. So the whole screen will appear to be uniformly illuminated. Even though there is interference, there is fringe pattern, but it changes so fast. Okay, it changes so fast that it appears as if there is no fringe pattern. Okay, and the whole screen appears uniformly illuminated. And what will be intensity? This is the intensity, average intensity over the whole screen. Simple addition, I1 plus I2. So in our case, it becomes 2 I naught. I naught plus I naught, it becomes 2 I naught. Okay. So that's it. We discussed intensity also. In the next class, we are going to solve some problems. And then we will discuss some other concept.